So how do we achieve this? How do we perform this classification? Again, we can divide things up. Always the way we can do things in many different ways. And one of the main divisions here we have in remote sensing is unsupervised versus supervised. The unsupervised method is perhaps the most tempting. It's the one we've tried so far on previous courses, certainly on the introductory course, where we let the computer do this spectral analysis, look for information in the image and say, right, I've found these classes, so-called unsupervised. But if we remember, once it was done, our work started. We had to tell the computer what each spectral class actually was. The supervised, here we do a lot of the work up front. We tell the computer what to look for, what things should look like, and then it does that for us and gives us then our information classes, because we've said this is what woodland looks like, or this is what water looks like. So how does this work? In all cases, we are going to be relying on band space. We'll start by exemplifying through unsupervised. So here we have an image. This is the near infrared false color composite. Behind it is the true color RGB behind. And I've picked out the 3 bands for this near infrared false color composite and put them as grayscale images here. And then this represents, it does, a 3D band space because we have 3 bands here. Getting a 4th band in is beyond, I mean, I'm struggling with this. Getting a 4th band in there would be beyond my skills in terms of graphics. So let's just rest here, see how well or badly this goes. So if we consider this pixel up here, which is a very big pixel, which for illustration, and then we try and plot this in this band space where we have the green light increasing in strength here, and we have red light and infrared light on the other 2 axes, increasing from an origin of 0. So when we try and plot this first pixel, we plot it into this band space. We ignore the information on where in the image it is, where in the aerial photograph it is. We are just interested in the value of the pixels in these different bands here, the different colors, how strong they are, and the strength of the signal increases out, and that places the pixel there. And we can move over to another pixel somewhere else and do the same thing and place the pixel out there. And we can see, well, hopefully we can see that is now 2 pixels placed out in band space. That one farther away from us. Yep, hopefully that's why it's smaller. I'm trying to get this sort of 3-dimensional illustration in here, and this one is closer to us, so it's a bit larger. We can continue this analysis across the whole image. We fill it up fill up the band space, or we pick out all of the pixels from the image and put them into the band space, not necessarily filling it, and we can see that they hopefully form these little clusters. And it's these clusters that we're interested in. This is what we're going to analyze. So moving away from my rudimentary illustration there, let's just go back to 2 bands because it's a lot easier to work with. So we have 2 bands, whichever 2 bands it is. This can be any of the colors that we've actually analyzed, infrared, red or blue and green, or whatever colors we're talking about here. There are many bands of infrared as well. This line here does not represent another band. This is no longer a 3rd axis. This is just simply it's 45 degrees, so it's the line showing where the values are equal on each band. And we have these 3 clusters here. So if the computer's going to make this analysis for us, we've taken all the pixels, we've plotted the values into our multi-dimensional space, however many we have. Here we're just looking at 2 to simplify things. They're existing there, and they're in these little clusters that we have a hard time visualizing because it's multi-band space, and they're in there. And we now need to begin this analysis. The computer needs to start identifying these clusters, seeing these clusters. We can see them in this 2D example. We can see them quite easily. The computer doesn't. It needs to do some sort of analysis. It needs to do a statistical analysis to find out, to get more information. It needs numbers on things. So it starts off by making a best guess. And in this case, the best guess, if we're looking at this particular version of doing things, we're just going to place out evenly spaced seeds. They're called seeds, and they're placed out evenly usually along this middle line here, where the values are equal in all axes. And it places out a number of seeds. Here we've used 3, just to keep things simple. Place out a number of seeds determined by us. We are in charge of this process. Even though this is unsupervised, it's not entirely unsupervised. We need to contribute a little to the process. So the computer after that is doing the work for us. So we have these 3 seeds, and then the next thing to do is to say, well, which one's closest? For each pixel, we look at a pixel and say, well, which seed am I closest to? And this one is quite evidently closest to the yellow. The next one, well, that's quite evidently closest to this bluey purpley thing here. And that one, well, yeah, but it's closer to the pink. We can see that. That's fine. So we do our classification. We reclassify all of the pixels as belonging to a particular seed. And then we say, well, the seeds, they are moved to their new locations. They become they get moved to the average position of those pixels that have been assigned to them. So the original position, the initial position of each seed is forgotten, it's lost, moved away, and the seeds are now moved to the average position of those pixels that have been classed as belonging to that seed. Well, that's simple, done. You can all go home, except not. What happens when we have this situation? So what's going to happen here? I mean, we put in our seeds again, and well, when we try and analyze that one, it looks a bit odd, because quite clearly the most logical for us would be that should end up down there and with this pink group. But when we look at this analysis here, it's closer to the yellow. So it actually ends up belonging to the same group as them. And that can't be right, can it? So what we need to do is start again, not from the beginning. We just iterate again over the process, because we have our seeds in here. Our seeds now look like this. You can see that yellow seed has moved out down to there because it's been pulled over by this one. Rather than being in there, it's now being pulled toward. I hope that's sort of the average. I'm kind of shooting from the hip. And so it's about there approximately. And that gives us our new seeds. So when we redo the analysis, we can now iterate over the whole thing again and say, well, which seed is each individual pixel closest to now? And I think we can see that these are going to stay closest to there, and those are going to be closest to that one. And that now, hopefully, when we redo that analysis, let's just have a quick look. Oh yeah, of course, it's closest to the pink seed there. And then we can move the seeds again in this iterative process. Now, that was just one problem that we solved there with this. So what we have to do is we just keep doing this over and over again until essentially we get bored, or we reach a threshold. You know, that we're saying, if every time I repeat this process of seeing which seed each pixel is closest to, if the change to the previous version of this is not that much, what not that much is up to us to decide in many respects, then I'll stop. You know, it's good enough. A lot of the times you want to go until the end, until nothing changes. And maybe you can do that, but you might find yourself in a situation where things just keep going backwards and forwards. You might end up with a pixel ping-ponging backwards and forwards between 2 different seeds. That can happen. So you might need to do another version of this, change the spacing of the seed, jitter it about a bit. Or we can use another method, for example, random seeds, where instead of evenly spacing these out, we just randomly seed out to begin with, and do the similar thing where we just look for the pixels, the seed that is closest to the pixel, and assign it to that. So when we do all this, we end up with another problem like that, which looks obviously ridiculous, because the seeds shouldn't be there. Those belong together. But it turns out that pixel there was closest to that seed rather than that seed. So we end up with a new average position for that pink seed, which actually is on that one pixel there, just in my illustration anyway. But then we just iterate again. We do the same thing as before. We iterate over the whole thing again and say, okay, reassess which seed are these pixels closest to, which one is these closest to, and so on. And we end up with a new classification that makes more sense. Good. Well, that wasn't too difficult. So, and again, we can, even with this random seed, we can end up with the same problem where when we have lots more data, rather than this very simple illustration, we might end up in a situation in some cases where things just ping pong backwards and forwards without ever fully resolving. We don't get to a perfect solution. Maybe we should tell the computer to give up after so many iterations. We can look at the image and see if it's good, or reseed it and start again, and then maybe it'll sort itself out. That might be okay then. So this is just something, it's unsupervised, but we still need to be there in the game. So to summarize the unsupervised classification, we are using a statistical analysis. We're using the mean of each group of pixels assigned to a specific seed. But how many seeds are we going to put in there to begin with? Well, this is something that we need to specify for the computer. It can't know, it doesn't know. And the number is essentially, there are different schools of thought on this. You should look for all the potential categories that you think you might be able to find in there, regardless of what your ontology is, what it is you're looking for. Yes and no, or you might just say, well, I'm only interested in this thing or that thing. It's either one, everything either belongs to this category or to that category, or somewhere in between that. You might have 6 or 7 categories that you're interested in. But generally for these unsupervised, even if you think you've covered this many classes, this is what I want, I should have this number of things in there. With the unsupervised classification, take that number of classes that you think should be in the image that you're interested in, multiply it by 3. It's just a rule of thumb, and allow the computer to look for that many classes. So if you think there are 7 classes in the image, multiply that by 3, which is 21, isn't it? Right, and so you end up with 21 seeds in the image, and the computer will try and look for that. And it will give you then some spectral classes, hopefully 21 spectral classes. And then you will have to assign those afterwards to information classes, which may be subclasses you will then need to collect together, or you may be able to directly assign spectral classes to one class. They may not need to be subclasses. You might just say there is this natural variation in the image. So the good thing about the unsupervised method is that it's, generally speaking, quick, at least to get going. You can get the image and say, well, it looks like this, go and do the analysis. And with large images, that can be an advantage because it can take a long time to analyze these things for the larger images. And it might also help you to identify things in the image that you weren't aware of, which is, you may not just, you've just not seen them, or it may be a new phenomenon, something new to you, which can happen. But you do have this problem then of having to identify what it is afterwards. And there might be spectral classes, as we've seen before, that are hard to identify, or they may not be entirely unique. The spectral class may be a mess and may belong to 2 information classes. There may be some sort of crossover between them. You may even miss, this is the kind of the problem, related problem here, you may miss an information class. You've done your analysis properly, there are 7 classes here and multiply by 3, but maybe one of your classes or several of your classes required several spectral classes, more than you expected, in order for them to become an information class. And that just didn't leave enough room over. There were no more seeds available to find this other information class that you can see in the image yourself. There just wasn't the capability left. So maybe you've missed something in that sense. That can happen. So there are always ups and downs. Unsupervised tends to be where we begin, especially as a novice. It may also just be the first step in a classification, where we then go on to do the supervised classification afterwards. We sort of do an initial survey, look what might be in the image, inform ourselves, and then do a supervised classification afterwards. Perhaps that's not always the case, but we might do.